This is my ISP design. It is a chess clock that can time a 1-minute, 5-minute, or 10-minute game of chess. This design demonstrates the capabilities of the shift register, an 8-bit memory IC built using latches. It can switch between two timers and also has a reset button. This is the most basic type of latch, the SR or set reset latch. It has two active low inputs, set and reset, and two outputs, Q and not Q. It uses NAND gates to create a latch system where the set input presents a 1 on output Q and the reset input resets it to a 0. Not Q, as its name suggests, is always in the opposite state of Q. The gated SR latch adds an enable pin using two more NAND gates, which disallows the latch from letting any data through when low, but allows data through when high. This is an improved design from the SR latch, but still presents a problem. This latch can be in illegal states. For example, if both set and reset are set high, it presents an unstable state. This problem can be solved by acknowledging the fact that reset always needs to be what set is not. There is no situation where they need to be both high or both low. Therefore, the reset input is removed and replaced with the set input run through a NOT gate. This is called a data latch or D latch. The D input controls both Q and not Q only when enable is high. The D flip-flop uses a two-latch system to turn the D latch into an edge-triggered latch. The first latch in the D flip-flop is called the master latch and is a D latch. It can let data pass through whenever enable is high. However, this data will not make it through the second latch, which is an SR latch called the slave latch, until a falling edge is detected on the enable input. This is the 1-bit memory storage design that is linked together to create the 8-bit shift register. In the shift register IC, there are two registers, the shift register and the latch register. The enable input is replaced with a clock so that data is constantly being pushed into the shift register, and a separate pin stores the shift register's current state in the latch register when high. There are three main parts to the code of this project: the setup, the calculation, and the display. The most notable part of the setup are the interrupts. These are two lines of code run in the setup function that will stop anything currently happening and run a certain function when a rising edge is detected on a certain pin. This is used to detect the button presses and determine which timer is paused, which is not, and to start the game if it is not yet started. Additionally, the starting time can be set to 10 minutes, 5 minutes, or 1 minute before the start. Once the first button is pressed, the game starts and the calculation begins. The elapsed time for each clock is calculated by subtracting the other clock's elapsed time from the total time since the game start. This is then subtracted from the maximum time to get each clock's remaining time in seconds. This is converted into minutes and seconds, and clock 2's remaining time is appended onto clock 1's to create an 8-digit number to be displayed across the two displays. The displays take advantage of persistence of vision, an optical illusion describing the eye's inability to see a change immediately after it happens. The digits are never on all at the same time, but they look as though they are to the naked eye. This illusion can be broken if a still image is taken of the displays. The display code uses a for loop that runs 8 times per iteration of the loop function, once for each digit pin. Firstly, the common anode for the correct digit is turned on. These common anodes are connected from the display directly to the Arduino. This isolates the place where the digit should be displayed. Next, the correct digit of the 8-digit integer is calculated. Finally, the 8-bit binary number corresponding to the digit is grabbed from a list of variables called an array to be sent to the shift register displaying the digit. A small delay is used to allow the display to register the data, and the common anode is turned off so that the next digit can be isolated on the next iteration of the for loop. This is the finished product, soldered onto a permaproto board. It is encased in a 3D printed case which contains a 9-volt battery to provide power to the circuit. meaning that his chess clock can function without the need for an external power source.